Okay, students, we're going to keep going down this rabbit hole and go further into our discussion of partition functions and the Boltzmann distribution. And we're going to use that to derive a famous equation called the Maxwell-Boltzmann distribution of speeds. So this will be on the heavy side. And as always, we will go through this in more detail in our live lecture. Okay. So our goal, first, we have to ask, what are we trying to do? Because we are often going to come up with these derivations in Chem, and it's easy to get lost with what we're doing. So our goal is to come up with an equation to describe a population of molecules with a specified velocity. Okay. So because our translational energy levels are very, very small in energy, there's going to be a wide population distribution to describe those. So we want to use this partition function to come up with an equation for that. And so now we have to take advantage, or we have to consider this idea called degeneracy or degenerate states, when two or more states have the same energy level. And as it were, if we think about the way a molecule might move in the x, y, or z dimension, those are all degenerate. So we're going to have to consider not like triple counting those things, right? So we first want to consider what we're going to use for our value of epsilon here. So we're going to use the kinetic energy given by its mass and velocity, because that's what we're interested in, the velocity. So we know that that's going to be described as 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared, where we know in the vector notation, the total velocity is the sum of all of the velocities, the squares in their respective dimensions. Okay, so that gives us the total velocity. Okay. We also need to consider that there might be triplicates, because we've got this XYZ thing going on. So we're going to come up with some function that has the following form, k, which I'm going to replace with this g. I know there's not enough letters in the alphabet, and I'm typically trying to use the standard letters that are available in text. So we're going to have an equation of the form f equals k e to the negative ek divided by kbt. Because remember, that beta term, right, is 1 over kbt. Beta is 1 over kbt. Okay, there it is. So now we can start plugging things in and expand on this a bit. And I'm going to rewrite e. So I often will, you see me write e as exp. And if, for example, I've got, let's say, e raised to the second power, I'm going to write that as exp bracket 2. So this is just like an example notation to make this a little bit easier to write, because I got to put all these equations up into that exponent. So this is going to be k. And now I'm going to write exp bracket, and there's going to be a negative sign. And now that's going to be 1/2 mvx plus 1/2 mvy squared plus 1/2 mvz squared. And that's all divided by kbt. And all of that is in the exponential. Okay. So we can do some algebra tricks here and simplify this expression as the following. So I'll write that as k times exp bracket negative mvx squared over 2 kbt. So I just put the 1/2 like so. And then let's see, instead of a bracket, I want to make that a parenthesis just to be less confusing. So parenthesis, parenthesis. Now we're going to have another parenthesis, exp, exponential of negative mvy squared, all divided by 2 kbt, and in bracket, because that's in the exponent, and in parenthesis. And then finally, hopefully you can see where this is going, exp negative mvz squared over 2 kbt bracket parenthesis. Okay. So we could further simplify this description by thinking of this as some function of velocity, where now we have functions describing what's going on in the x, we have a function what's describing going on in the y, and we have a function describing what's going on in the z. Okay. And of course, we've got this constant k out in front that we've got to deal with. So that's our next goal, is to find that constant k. And we're going to do that by invoking the language of calculus. So I'm going to write a dv on this side and a dv on this side. And what I want to note here is if we integrate f of v dv, okay, so for example, if, and I can play with this in all the dimensions or just any one dimension. So let's just play with it in one dimension for now by writing f of vx dvx equals k, and that's k only in the x dimension. So we can see we could distribute that k through all of these functions. And f of vx dvx. So all I did was separate out any one of those things. Okay. So if we integrate both sides from negative infinity to positive infinity, we know that we're going to get 1. So that's kind of a way of saying if I integrate this whole function across all of space, negative infinity to infinity, I get 1, or in other words, 100% of the population, right? And now I'm going to supply what we know from the other equations that we developed right here. So now we've got that kx component, and then we know the rest of that is going to be exp negative mvx squared over 2 kbt. And of course, we could come up with the exact same expression for any one of these things. Okay. So now, noting that we've got still an integral to take over here, right? So I integrated this, and this went away. However, I still have to integrate all of this. So integrate from negative infinity to positive infinity of dvx. And we would find that if we were to integrate this expression, it does have a standard integral. That standard integral is the following. So negative infinity to positive infinity of the function, the exponential of negative ax squared times dx. And let's just stop for a minute and compare these two things, right? So this is like from my standard integral table. So my x squared is my vx squared, and a would be the constants m2, kb, and t. And then we note because this k is a constant, it's going to come out in front of the other side. So the standard solution for this integral, it's very simple. It's just pi divided by a to the 1/2 power. So now we can take that standard solution and plug it into here and get a more exact expression. So let's do that on the next slide. So I've got a whole blank slide here. Okay. So we established that 1 equals kx. And then now we've got to apply my constants m, 2, kb, and t into a. And what we come up with is the following. So that ends up being 1 equals kx times 2 pi. Let me make that parenthesis a little bit easier to read. So 2 pi times kbt, all divided by m, and that's to the 1/2 power. So finally, we can rearrange this and solve for what kx should be, or really any of the k's in any of the dimensions, right? Because they're all going to be degenerate. And so we come up with the following. So just flip that around. So that's going to be m over 2 pi kbt. And let's see, we divided that out. So that's still to the 1/2 power. And now noting here, when we put all of this together, if we go back here, so I said K times all of this other stuff, and then we separated one of those K's for just dvx. So in other words, what we did was kind of said, okay, kx times ky times kz should equal this big K. Well, we could repeat this in any one dimension, and we would get the exact same thing. So plugging all of those back in, you can see it would be kx times ky times kz, which is the same thing. So now we can say k is just m over 2 pi kbt to the 3 halves power, right? So we just cubed it, okay? And now plugging all of this back into what we have, we can get the following. So we can say now f of v dv, which now corresponds to all of our velocities and all of the dimensions, is going to be equal to m over 2 pi kbt to the 3 halves power. Okay, and then now that's going to be times the exponential of negative m, and I'm going to do a little trick here. I'm going to write negative m just v squared all over 2 kbt. Where now recall my v squared is just vx squared plus vy squared plus vz squared. So I could plug these all back into this exponential just like I did, and then they will all collapse into one single exponential using the properties of exponentials. And of course, that is still now going to be multiplied by dv. And to make a point here, I'm going to make sure we recognize that's dvx, dvy, dvz. So we're dealing with a volume element here. Okay. So we're almost there coming up with this equation. We just now have to figure out how to eliminate all of these things. And we can't just simply say dv will equal dvx, dvy, dvz. They're actually related to each other from the volume element. So the way that goes is the following. So let me make sure I'm doing this all correctly here. So we can replace this dvx, dvy, dvz with the following. So that becomes 4 pi v squared dv, integrated from negative infinity to positive infinity. And that, if we set equal to just dv, integrated from negative infinity to positive infinity, then we've come up with the volume element of a sphere, right? So if we finish integrating this thing, you get 4/3 pi v cubed, right? Which is the volume of a sphere. So now we can replace all of that, and the only factors we will need are the v squared and the 4 pi. So if we include that, our dv's and our dv's will cancel. So let's write all that out. So that becomes f of v dv equals this constant m 2 pi kbt to the 3 halves power times exponential of negative mv squared over 2 kbt. And then now that becomes times 4 pi v squared dv. Okay, and if we integrate those volume elements, we end up with the following. F of v, so what we're really trying to do is just eliminate the dv and the dv. So I'm going to bring those out in front. And what we are left with is the following. 4 pi m 2 pi kbt to the 3 halves v squared, we've got to include that v squared, exponential negative mv squared over 2 kbt. And there we have it. This becomes our Maxwell-Boltzmann distribution of velocities. So this will give us the fraction of molecules with velocity v at temperature T. Whew, that was a lot of stuff to go through. We will go through the properties of this equation in the next slide.